This video covers the shear failure of the reinforced concrete beams. The reinforced concrete beam is subjected to both bending moment and shear forces. In the last series of videos, we have looked into design of a reinforced concrete beam for the bending moment. But apart from the bending moment, we also have shear forces in the reinforced concrete beams, and we need to design the beam to take these shear stresses as well. The typical characteristics of a shear failure is a large diagonal cracks, as you can see here. The diagonal cracks extends from the tension region up to the compression region, and the shear failure is governed by both the tensile strength of the concrete as well as the compressive strength of the concrete. That is why the shear failures are very abrupt and catastrophic, and we don't want the structures to fail in a catastrophic nature like this one. This picture is from the Wenchuan earthquake in 2008, and we can see a reinforced concrete beam has failed due to shear here. Now let's have a look at how the shear failure looks like. The detail of this video and the experimental setup is given in another video in the link below. So as you can see, the shear failure is very brittle and abrupt, and there was not much deflection in the beam before it fell very catastrophically and very abruptly. If you look into the midspan moment and the midspan deflection plot for this beam, you can see it's a very brittle failure. As soon as the beam reaches its maximum moment capacity, that is around 38 kN/meter, the beam abruptly fails. There is no yielding of the beam, there is no yielding of the steel reinforcement for this beam. It is a very abrupt, very brittle failure. And also we can see that the midspan deflection is very small. It is just around 20 millimeter. The shear failure in the reinforced concrete beam is characterized by a large diagonal cracks in the shear span where the shear force is maximum. There is not much deflection in the beam, so you cannot get enough warning when these kind of structures fail. And the failure is very catastrophic and brittle. We don't want our structures to be failing in this kind of manner. Compared to the flexural failure that we saw in the previous videos, the flexural failure is very ductile kind of failure. We can see large vertical cracks. Here the steel yields before the concrete crushes, making it a ductile failure. If we look into the beam subjected to 4-point loading, the vertical cracks in the maximum moment region, these are the flexural cracks, whereas the diagonal cracks in the shear span, these are the shear cracks. So again, if we draw the shear force diagram and bending moment diagram for this simply supported beam subjected to 4-point loading, we know that the shear force diagram will look like this one. The shear force is maximum in the shear span on either side, and in the middle between the loads, the shear force is 0. And if we draw the bending moment diagram, where the shear force is 0, the bending moment is maximum and it is constant in this region. Now in the shear span, where the shear force is maximum, we have both the shear force and the bending moment acting in this region. There is a shear force as well as there is a bending moment acting in this region. Whereas in the constant moment region, there is only the bending moment acting in here. There is no shear force acting in there. Now if we take a section BB in the constant moment region, we know that there is no shear force acting in there. Only the bending moment has the effect there. And the bending moment causes the bending stress at the section BB. If the loads are small and if the beam is still in the elastic region, the bending stress are still very small and they are linear, still linear. So at the bottom it is tensile stress and at the top it is compressive stress. However, if we take a section AA in the shear span, we know that there is effect of both shear force and the bending moment as well. So this is the bending stress caused by the bending moment, and this is the shear stress on the transverse face of the beam. So again, at section BB, where there is only bending moment acting on it, so there is only the normal stress caused by the bending moment, whereas at section AA, there is both bending stress and the shear stress caused by the shear force as well. So the bending moment causes the normal bending stresses in the beam. At the bottom it is tension and at the top it is compression, whereas the transverse shear force causes the transverse shear stress in the beam cross section. So in this video, we'll look into how we design the beam for this transverse shear stresses. If we look at this, example, a cantilever beam subjected to the shear force, we see that the shear force tends to deform the cross section of the beam. But if you look closer here, the top and bottom cubes in this beam are not deformed here yet, because the shear stress and the shear strain at the top and the bottom are zero. However, the shear stress and the shear strain is maximum at the middle of the beam. Therefore, the deformation of this cube is maximum at the middle as well. Because of this nonlinear distribution of the shear stress in the cross section, the shear strain will make the beam warp. Therefore, the assumption made in the Flexural formula that the plane section remains plane and remains perpendicular to the deformed axis is no longer valid here. However, for slender beams, cross-sectional warping due to the shear strain is assumed small, and we assume that it doesn't have effect on the distribution of the flexural stresses in the beam. So if we take a small element in the constant moment region, we see that it is subjected to normal stresses due to bending moment. And as this is in the tension region, we will have normal tensile stresses in this beam denoted by sigma. However, if we take a small element in the shear span, this element is subjected not only to the normal stresses due to bending, but there will also be the transverse shear stress due to the shear force as well. To balance this transverse shear force, there has to be another transverse shear force in the opposite direction. And to balance this couple, there has to be a shear stress in the longitudinal face of this element as well. Now, if we rotate this element at certain angle, this element will be subjected to pure tensile stress and the compressive stress only, and it is called as the principal tensile stress and principal compressive stress. So if we rotate this element at certain angle, this element is only subjected to principal tensile stress and principal compressive stress denoted by sigma 1 and sigma 2 respectively. Now, the concrete is strong in compression, so it can take the principal compressive stress. However, when the principal tensile stress in this direction exceeds the tensile strength of the concrete, it will crack. Now, if we draw the bending stress and shear stress profile at section A, the bending stress is as seen here. It is on crack section, so the stresses are still linear. At bottom, it is a tensile stress, and at top, it is a compressive stress. The shear stress distribution will be parabolic like here. The shear stress at the bottom and the top is 0, and it will be maximum at the middle of the beam at the neutral axis. The transverse shear stress, as we know, is given by tau equals to VQ over IB, where V is the shear force acting at that section, Q is the first moment of area about the neutral axis, I is the moment of inertia, and B is the width of the beam. Q, the first moment of inertia, is maximum at the middle of the beam, and which is given by BD squared by 8. So if we plug in the maximum Q in the shear equation, we get the maximum shear force in the middle of the beam is 1.5 times V shear force divided by the cross-section area A. Now, when we keep on increasing the load, the reinforced beam will crack, and the tension stresses at the bottom will be taken by the steel, and the stress distribution in the concrete becomes nonlinear, as we know. And the shear stress distribution will look like this for the cracked reinforced concrete beam. Up to the neutral axis, the shear stress distribution is parabolic, and below the neutral axis, where all the tensile stresses are now taken by the steel, the shear stress in the concrete section is constant, and it is tau max. So for the cracked reinforced concrete beam, the average shear stress tau can be computed by this equation, that is V shear force divided by BW, which is the width of the beam, and Z, that is the lever arm between the compressive force and the tensile force. Or simply we can write the average shear stress as the shear force V divided by BW, the width of the beam, and dV, where dV stands for the effective shear depth of the beam. AS3600 clause 8.2.1.9 gives the equation for dV. dV, or the effective shear depth of the beam, is taken as the greater of 0.72 d or 0.9 small d, where the capital D is overall depth of the beam and the small d is the effective depth of the beam up to the center of the reinforcement. Now if it is a T-beam, the average shear stress equation still holds true. Tau is equal to V divided by BW dV, where BW is the width of the wave of the T-beam. dV is again the greater of 0.72 d or 0.9 d. So if we look into the shear span of a beam, particularly subjected to high shear forces, the angle of the principal tensile stress is around 45 degrees to the horizontal. Therefore, the diagonal shear cracks occur at around 45-degree angle. So if we look into a relatively shorter beam without any shear reinforcements, there can be three different kinds of shear failure mode. The first one we call it as a diagonal tension failure. Second one is called as a shear compression failure, and the final one is a deep beam failure. The mode of this failure depends on the shear span to the effective depth ratio. The shear span here is A, denoted by A, and the effective ratio is D. Depending on A over D ratio, one of these shear failure can occur in relatively shorter beams. The first one is the diagonal tension failure. This type of failure occurs for slender beams where A over D, or the shear span length divided by the effective depth D, is between 6 to 2.5. It is relatively slender beams. In this kind of failure mode, first the diagonal cracks appear, and as there are no shear reinforcement in this beam, the concrete will crack, and the diagonal crack extends from the tension region to the compression region, and the beam will abruptly fail. And this kind of failure is called as diagonal tension failure. The second type of failure is called as a shear compression failure. This kind of shear failure occurs in a relatively shorter beams where A over D, the shear span over effective depth ratio, is between 2.5 to 1.0. So in this kind of failure as well, the diagonal cracks will first form. They will try to extend to the compression side. As the shear span is relatively short, this diagonal cracks will come under the loading point, so it cannot extend to the compression side. Instead of that, it will try to bend. The diagonal cracks from both sides will form an arch mechanism in the beam. And as the arch is formed, the beam can take more load. And the beam will finally fail due to the crushing of the arch at the compression. And this kind of failure is called as shear compression failure. The final type of shear failure mode is called as a deep beam failure. This kind of failure occurs when A over D is less than 1. It is a very short and deep beam. In this kind of failure mechanism, the arch with more height is formed under the loading point, and the tension reinforcement will act as a tension tie for the arch here. This mechanism is called as a tight arch shear resisting mechanism, and it can resist further load. The beam will finally fail when the crushing occurs at the strut due to the diagonal compression. This kind of failure is called as the deep beam failure. Hence, the shear failure modes for the beams without shear reinforcement will depend on the A over D ratio. If the A over D ratio is less than 1, it will be a deep beam failure. If A over D ratio is between 1 and 2.5, we will have a shear compression failure. As you can see, there is a crushing of the arch in the compression. And if A over D ratio is greater than 2.5 up to 6, it will have a diagonal tension failure. As you can see, there is a big diagonal crack extending from the tension side to the compression side. And if A over D ratio is greater than 6, the beam will have a flexural failure. As you can see here, there are a large number of vertical cracks, the steel will yield, and finally the concrete will crush in compression.